Okay, so welcome to the first online class of functional. This be a little weird, but anyways, we'll try to do whatever we can for now, and then see how we adjust as we need. Okay, so last class we were looking at Hilbert spaces. Hilbert spaces, which are complete inner product vector spaces. So one of the things that we've seen is that these guys have orthonormal basis. Okay, and this is a segue, or it comes out of the projection theorem. But today we'll actually be looking at something that has slightly less structure, which is Banach spaces. Okay, these guys are complete normed vector spaces. Okay, and they do not have a concept of orthonormal basis. Okay, so the idea is that these guys do not clearly admit a projection. Okay, so one can take the infimum, but as I mentioned in the proof of the projection theorem, this is not always going to be convergent. The sequence that we get is not always going to be convergent. Okay, so let's go again. What is a normed spaces? Okay, so the definition of a norm. Norm. It's this functional that has the following properties. The norm of x has to be bigger or equal than 0 for every x in the vector space x. The second one is that the norm of x is equal to 0 if and only if x is equal to 0. And number 3 is that alpha times x norm is equal to the modulus of alpha times the norm of x for every alpha in R or C. And number 4 is the triangle inequality, which is something we need to remember all the time. X plus y is less or equal than x plus y. Okay, so this is all the structure that we're going to be asking from our spaces, that they have a norm, and the norm satisfies all of these properties. Okay, so one thing that we should start talking about is the difference between vector spaces with finite dimensional vector spaces and infinite dimensional vector spaces. Okay, so let's talk about differences between. I mentioned these things, but it's good to go over them again, because once you understand really the difference between them, then you can start understanding what type of things you can extrapolate and which ones you can't. So between finite dimensional and infinite dimensional vector spaces. Okay, so one of the things is that one of the things is that for finite dimensional vector spaces, all of the norms are equivalent. Okay, so let's put a theorem. Assume the dimension of our vector space X is equal to n, then any norm is equivalent to each other. Okay, so okay, let's say that X has a basis, X has a basis E1 through En. Then one of the things that we had said is that, okay, so if we have a basis E1 through En, we would have that we can write for every X in X, there exists lambda 1 through lambda n, such that X is equal to the sum of, let's say, I equals to 1 up to n of lambda I ei. Okay, so this is the representation of X in our basis E1, E1. And so we talked about before the different P norms. Okay, so the P norm of X is just the sum of lambda I to the P to the 1 over P. Okay, but I mean, this is not necessarily all the norms that you can take. You can take any convex function here and the inverse of it outside. So we could take something like, let's say we take a convex function here. It has to have a few more properties, but morally this is the idea. You take, if I remember correctly, you take phi of lambda I, and then you would take something like phi inverse of lambda I, and then you play with these kind of things, and this guy induces a norm in X. Okay, I'm not going to show this, but the point is this is a type of norm, but you could actually think of norms that are a bit more complicated that are still the same. So, but the point of this theorem is no matter what norm you come up with, so the examples here is P equals to 1, P equals to 2, and then you have P equals to infinity, which is the supremum of lambda I. So in a previous class we talked about how you can show that all of these guys are equivalent by basically playing a bit with them. So the point is, this theorem is telling you all of the norms are equivalent. Okay, so in particular the topology given by the natural topology of P equals to 2 is the topology for every other norm. Okay, and this is something that is not true for infinite dimensional spaces. Okay, and that's sort of one of the main differences between these things. Okay, so let's keep going a bit. Okay, so let's try to prove the previous theorem. So let's go for a proof. So let's divide this here. Okay, so let's take the star norm, a generic norm in X, and consider the 2 norm, and so let's take star, a generic norm in X, and we will show that it is equivalent to the 2 norm, which I defined before. Okay, so the point is, if you have that the star norm is equivalent to the 2 norm, and then you have another norm which is also equivalent to the 2 norm, they are all equivalent in each other. So this is enough this is enough to show the theorem. Okay, so how we will do this? This is a bit similar to what we done between the infinity norm and the 2 norm, but let's do it again. So we are going to set m, which is equal to the sum of I equals to 1 up to n of the star norm of EI squared to the 1/2. Okay, so now we would take x star, which is the sum of lambda I EI star. Okay, but now we use the triangle inequality to say that this is less or equal than the sum from I equals to 1 up to n of lambda I EI star. But in particular, using the property of the norm, this is just equal to the sum from I equals to 1 up to n of the modulus of lambda I times EI star. Okay, and now here we apply Cauchy-Schwarz. So by Cauchy-Schwarz, this is the sum from I equals to 1 up to n of lambda I squared to the 1/2 times the sum of I equals to 1 up to n of EI star squared to the 1/2. Okay, so the point is that we define m to be the sum of these guys here, just because here we are going to get that this is less or equal than m times the norm of x2. Okay? All right, so this shows one side of the equivalence. So I guess I didn't say it before, but equivalence is showing that there exists. So the norm star is equivalent to the norm 2 if there exists m and m and little m such that little m times x2 is less or equal than x star, which is less or equal than m x2. Okay, so what we just shown is the right hand side of this inequality, and we need to prove the left hand side. So the point is, if you can find these m and little m's, then we can show that the topology induced by this norm and the topology induced by this norm are equivalent. Okay, so now let's try to find where does this little m come out of. Okay, so we are going to consider the function. So let's consider, so now let's try to find little m. So we are going to consider the function f, so let's call it little f, which is going from, let's say in this case, Rn to R, which is given as a function of the coordinates. So f of lambda 1 lambda n is equal to the star norm of the vector with those coordinates, lambda I EI star. Okay, so what are we going to show? So the point is, I mean, we define this function, but what do we want to use? We want to show f is continuous with respect to the usual topology in Rn. Okay? Hence, it achieves its infimum over closed bounded sets. Okay, so this is the first part, this is the second part, and then we are going to use that it achieves its infimum. So we're going to define little m to be the infimum of, let's say, lambda 1 through lambda n in the unit sphere, Sn minus 1, of f of lambda 1 through lambda n. Okay, so this infimum, which we know it's going to be different from 0, and we'll show that now. So if we know that this infimum is less or equal than 0, we actually can use this m for this part here, this little m for this part here. So why do we know that the infimum is different from 0? So, okay, so assume little m is equal to 0, then there exists mu1 through mu n, which are in Sn minus 1, such that f of mu1 through mu n is equal to 0, because f is continuous. And we'll show the continuity in a second. But if f of mu1 mu n is equal to 0, this implies that the star norm of mu I, so the sum of I mu I in the star norm, is equal to 0. But this implies that the sum of mu I EI is equal to 0, because of the properties of the norm we looked at before. And if this is equal to 0, this implies that mu I is equal to 0 for every I, which implies that mu I is not, so the vector mu I is not in Sn minus 1. Okay, so this is a contradiction. So this is a contradiction that came out of assuming that m is equal to 0. Okay, so therefore m is strictly bigger than 0, and this implies that for every x, so for given x such that the norm of x2 is equal to 1, then the norm of x2 is equal to 1 is equivalent to lambda 1 lambda n in Sn minus 1, which then this implies that the norm of x star is bigger or equal than m. Okay, and this is exactly why we were taking the infimum of this function over Sn minus 1. Okay, so then for a generic x different from 0, we consider x over x norm 2, which is in Sn minus 1, which then implies that the norm x, the star norm of x over x2 is bigger or equal than m, and this implies the norm of x star is bigger or equal than m, the norm x2. Okay, so now what we are missing to show, to finish the proof, we need to show that f is continuous. Okay, so we'll show a bit more. We'll even show that it's Lipschitz continuous. And how do we do this? Okay, so let's take f of lambda 1 through lambda n minus f of mu 1 mu n, and we take the absolute value. What is this? This is equal to the absolute value of the sum of lambda I ei in the star norm minus the sum of mu I ei in the star norm. But at the same time, this is less or equal, and this is by the triangle inequality. This is less or equal than the norm of the sum of lambda I ei minus mu I ei. And this is in the star norm. Okay, and now we do the same bound as we did before. So we do the same bound as we did here to obtain that this is less or equal than the sum of lambda I minus mu I squared to the 1/2 times the sum of ei star squared to the 1/2. Okay, so this is less or equal than, well, this is equal to m times the two distance between the vector lambda 1 lambda n minus mu 1 mu n. Okay, so this function is actually Lipschitz continuous, which is what we needed to show in this step here. And so we can show that we obtain a little m, which is the bound for, which is this bound for this guy. Okay, so this is a bit of a thing that I've been mentioning. So for finite dimensional spaces, all of the induced topologies are equivalent to the standard topology. So for finite dimensional norm spaces, okay, so one of the main things that changes when we go to infinite dimensional things is the lack of the following theorem. So theorem, which is usually called Hein-Borel. Any closed bounded set of a finite dimensional, of a normed finite dimensional So now space is compact. Okay, so what are we going to see? Okay, so this is what is the proof of this? The proof of this is just that all of these topologies are equivalent. So in particular, this is true for the standard topology. Hence, it's going to be true for this topology as well. Okay, and what are we going to do now? Just to start seeing what is the main difference with general spaces. So we've seen this for, I think, for the Hilbert space case, but let's do it again in the Banach space case because it's a bit different. Theorem. If X is an infinite dimensional normed vector space, then neither, so let's say B1, which is equal to the X in X such that the norm of X is less or equal than 1, nor let's call it S1, which is equal to the X in X of the norm of X is equal to 1, then neither B1 nor S1 are compact. Okay, so the main point is once we are in the infinite dimensional space, whenever we take a norm, the norm will make that our unit ball or our unit sphere are not compact. Okay, so if X is an infinite dimensional normed vector space, then both, I don't like this, then both B1 and S1 are not compact. Okay. So what is the proof of this? The proof of this uses something that is called Riesz lemma. Okay, so we'll prove first Riesz lemma and then we'll come back of how to show this. So morally, what do we have to do here? To prove this theorem is we need to find a sequence of points that does not induce as a convergent subsequence. Okay, so you have to find a sequence of points that are all separated. Okay, you cannot find any subsequence that works. So Riesz lemma gives you an idea of how to construct this. So if X is a normed vector space, comma, and Y is a closed subspace such that Y is different from X, then for every real number, for any, let's put it like this, then for any alpha between 0 and 1, there exists X alpha in X such that X alpha is in the unit sphere and X alpha minus Y is bigger than alpha for every element in your subspace Y. Okay, so let's try to do the proof of this. Then after we do the proof of this, the proof of the theorem will be simple. Okay, so let's do the proof of the lemma. Proof of the lemma. Okay, so first, because there exists what did I wanted to say? Because there exists because x minus y is different from the empty set, then there exists x which is different, x which is not in y. Okay? There exists x in x in x, such that x is not in y. Okay, but what does this imply? So this implies that the infimum of the distance, so the infimum of, let's say, y in y of x minus y is equal to, let's call it a parameter gamma, which is bigger than 0. Okay, so this implication is because y is closed. Okay, so because y is closed, we have that this infimum has to be positive. Because if this infimum is equal to 0, then that means that there is a sequence of points in y such that they converge to x. But if they converge to x, using that y is closed, x belongs to y. Okay, and we have assumed that x is not in y. All right, so then what do? We fix alpha in 0, 1, and we have that gamma is less than gamma times alpha to the minus 1. This implies, okay, so because gamma is the infimum of x minus y, then this implies that then there exists, and let's call this y alpha, such that x minus y alpha is going to be less than gamma times alpha minus 1. Okay? Because this is slightly larger than the infimum, I can always find a point that is less than this. Okay, and so now the point is that we have taken the projection of x onto the direction of y. Okay? So let's try to draw a picture, but I'm not sure this is going to be helpful. So what we have done is, let's say that we have a closed subspace, which is this direction here, y, and we have taken a random x here. Okay, this is our x. So we know that x is not in y's, but this distance here could be tiny. So the question is, how do we make so that we choose an x which is in that direction? Okay, so it's like basically in the direction that is perpendicular to y. So one of the points is we don't have the notion of perpendicularity because we don't have the inner product. Okay, no inner product. But the idea is that we can still take some sort of projection by minimizing over, by taking these infimums here. Okay, So we are not saying that the infimum exists, okay? And that's the main difference between Hilbert spaces and Banach spaces. In Hilbert spaces, what we can say is that there exists a minimum. Here, we can just say that this is positive, okay? So then, now for this alpha in 0, 1, you take one point which is going to be close to the projection. So it's not going to be that point here, but it's going to be a point which is close to there. So now when we take x minus y alpha, we are going to get a vector which, if we project here, is almost perpendicular to y, okay? So the vector x alpha that we're going to choose is going to be x minus y alpha, x minus y alpha without the norm, over x minus y alpha, okay? So the idea is that once we normalize this, we are going to get a direction in the unit sphere which is almost perpendicular to the direction of y. All right? So it's not that this is exactly perpendicular. It would be exactly perpendicular if we had taken the projection, okay? But because we don't have convergent subsequences, because we do not know that the subsequence is going to converge, we cannot actually take a projection exactly. So this is an almost projection, let's say. So this is an almost proof. So now let's show that x alpha, let's show that x alpha satisfies the desired property. Okay, so how do we show that? So we take x alpha minus y, where y is any vector. So we take y in y, and we take x alpha minus y. So now we develop x alpha. We develop x alpha, and we get that this is equal to x over x minus y alpha minus y alpha x minus y alpha plus, minus, and y, and I'm going to make appear x minus y alpha on top and divide by x minus y alpha. Okay, so now the idea is everything is being divided by x minus y alpha, so this is equal to 1 over x minus y alpha times x minus y alpha minus, okay, so let's put it like this, minus y alpha plus y x minus y alpha. Okay, so this seems a little strange, but now we have a bound of 1 over x minus y alpha, which is coming by the choice of y alpha here, which has to do with taking the almost projection of this guy. And here, this vector here is going to be in y, because this is a vector in y, and this is a vector in y, and this is because y is a subspace. Okay, so whenever we take linear combinations of vectors in y, we are going to get a vector in y. Okay, so now what can we say? This guy is going to be bigger or equal, because I am flipping the norm here. This is going to be bigger or equal than 1 over gamma alpha minus 1, which is alpha times gamma inverse. And at the same time, the property of x is that x, the infimum of x minus y, is bigger than gamma, so it's equal to gamma. So here we have this guy becomes this, and this guy is bigger or equal than gamma. So in particular, this is equal to alpha. Okay, and this guy x alpha belongs to the unit sphere. X alpha in norm is equal to 1. Okay, so looking back at the picture, this guy is not exactly perpendicular, but it's almost exactly perpendicular. Okay, so if we take alpha all the way going to 1, then we would have something there. Okay, the point is what would want to do is, like, if you would want to find the perpendicular, you would take the sequence x alpha where alpha is going to 1, and now I want to show that x alpha is compact and find a limit for this guy. But x alpha is not compact. Okay, and this is what we are going to show now, which is the theorem that I was talking about before. If X is an infinite dimensional non-vector space, these sets are not compact. Okay, so both the unit ball and the unit sphere are not compact. Okay, so how do we show this? We're going to be using Riesz theorem. Okay, so proof of the theorem. Proof of the theorem. We take x1 in the unit sphere. Okay, so let's call it S1. Okay, so now by pick alpha equals to 3/4, and then by Riesz lemma, there exists x2 in S1 such that the norm of x2 minus alpha x1 is bigger than 3/4 for any alpha in R. But in particular, okay, this implies that x2 minus x1 is bigger than 3/4. Okay, so now I take one point, I take another point, which is at a positive distance. Okay, now let's consider y, which is equal to the span of x1 and x2. Okay, this is a closed vector space. So here, I mean, if you realize what I'm doing here, this guy here is also, this is the span of x1. So we take y to be the span of x1 and x2, which is a closed vector space. So then again, by Riesz lemma, there exists x3. Okay, so one of the things that we are using implicitly is that we know that X is an infinite dimensional space. So if X is an infinite dimensional space, we know that this is different from X. Okay, so the span of two vectors cannot be X, if not it would be finite dimensional. So by Riesz lemma, there exists X3 in X such that X3 minus, let's say, alpha x1 minus beta x2 is bigger than 3/4 for every alpha comma beta in R. So in particular, x3 minus x2 is bigger than 3/4, and x3 minus x1 is bigger than 3/4. Okay, so the point is, we repeat this process inductively. And we find xn in S1 such that, okay, so this is a sequence xn in n, which is a subset of S1, such that xn minus xm in norm is bigger than 3/4 for every n and m. Okay, so for every m different from m. Okay, therefore xn and in n does not admit any convergent subsequence. Okay, so if you had a convergent subsequence, you need to be Cauchy, but this property here prevents that any subsequence is Cauchy. Okay, so this kills any sort of convergence that you might have. So in particular, what we have shown is that we can find sequence which is we can find a sequence in S1 which has does not admit any convergent subsequence. So in particular, therefore B1 and S1 are not compact. Okay, so this is what I wanted to do for this today in this class. Next class we'll start looking at operators and hopefully some other interesting stuff. Okay, see you.